This is a recording of a presentation originally given to a seminar in November 2011 in which Oasys software for geotechnical design was presented in relation to the use of Eurocode 7. My name's Brian Simpson. I'm an ARUP Fellow and a Director of ARUP of the Geotechnical Group in ARUPS, and I have had a long relationship with Eurocode 7, being involved in its development since the early 1980s. This presentation will look at Eurocodes and the related developments, the related documents, all the documents used in Europe for geotechnical design. Then looking into Eurocode 7, the basis of geotechnical design, and a little about the design of spread foundations and retaining structures. Firstly, the Eurocode system itself. The Eurocodes are a set of design codes written for standardizing the design of buildings and civil engineering structures. As we'll see, there are other codes that relate to construction, but these are the design codes. Eurocode basis of design, they don't like it to be called Eurocode 0, sets out the general principles of the system and provides all the definitions of terminology, so it's important that anybody working with the Eurocode system has basis of design available to them. Much of its information is not repeated in the other codes. Then Eurocode 1 deals with actions or loads on structures, 2 is for concrete structures, 3 for steel structures, and so on, down to Eurocode 7, geotechnical design. There's a separate Eurocode 8 for seismic design, and Eurocode 9 is for aluminium alloy structures. There's talk now of a Eurocode 10, possibly on reinforced glass structures. Eurocodes are the design standards, but besides those there's a whole series of other documents under development or largely now completed which have to be used together with the Eurocodes. In the middle of the slide here we think about the geotechnical project. That will use Eurocode 7 up at the top, and it will also use other Eurocodes that are down at the bottom of the picture there, the structural Eurocode. So if you're designing a pile or a retaining wall, you'll need both the geotechnical code and the structural code. In addition to those design standards, there are other documents that we will briefly think about for execution and for investigation of the ground, for example. So if we start with execution, what does that mean? This picture shows an execution. It's one of two words that really are used with a slightly different meaning from their normal English meaning. An execution just means construction. In Eurocode you execute the design, construct the project. Hopefully you don't execute the designer. So here are the execution codes. These are documents that tell constructors how to carry out the construction of board piles, ground anchors, diaphragm walls, various types of piling, and so on. Deep mixing down the bottom of the list there, vertical drainage. A whole series of codes. They're all in use and they're the European documents. Some of them are being revised gradually. The ground anchors one in particular, a new revision of that will come out quite shortly. Over on the other side of the picture we have documents about ground properties, classification and description of the ground, and testing. Many of these are being developed jointly between the European Standards Organisation, CEN, and the International Standards Organisation. So they're ISO codes as well as CEN codes. Here's a list of some of those, most of those, and they vary as to how they're being adopted. So far they're in the process of being adopted in Britain. So you can see that the top few, for instance, are already current British standards. EN ISO 14688-1, identification of soil, is a British standard. It's now the British standard for identification of soil, and 14688-2 is the British standard for classification of soil. BS 5930 still exists, and in fact has been completely revised so as to be consistent with these documents, so that BS 5930 adds quite a lot of additional information, but is entirely consistent. Further down the list, we have EN ISO 22475-2, qualification of people carrying out sampling, and -3 is conformity of the equipment and so on with the code. These are slightly unusual in their adoption in Britain, in that the Eurocode 7 Part 2 says that they should be followed in UK practice. So it's really requiring, for the first time, requiring a qualification methodology for personnel involved in ground investigation. EN ISO 20476 has a lot of sections dealing with individual types of soil testing, and some of those are already current British standards, replacing parts of BS 1377 which have been withdrawn. So, for example, the existing BS 1377 on the standard penetration test is now withdrawn. Further down here we have some so-called technical specifications. They were initial attempts at standardizing which weren't adopted in Britain, in fact weren't published by BSI at all, because they were thought to be inferior to existing British standards, but they're now being revised under British chairmanship, and I'm sure will become British standards before very long. A particular code of importance will be 22477-5 on testing of anchorages. There's a series of them under this 22477 number on testing, pile load testing and so on, which have not made very much progress yet, but the anchorage testing is an important one. It is under development, and we hope that shortly that, together with the execution code EN 1537 and a revised section 8 for Eurocode 7, will come out together, providing a complete suite for design, construction and testing of ground anchors. So those are some of the ground investigation documents. Over in the bottom left-hand corner of this diagram we have NCCI. These are the so-called non-conflicting complementary information. Each Eurocode is allowed to name some information of this type, non-conflicting complementary information. A particular one that's been written for British use is PD 6694-1, but Eurocode 7 itself lists as non-conflicting complementary information various other documents, and let's just have a look at what those are. BSI have invented a new term just called published documents. They're not allowed to call them standards, and they have this sort of complementary function. So published document 6694-1 is recommendations for the design of structures subject to traffic loading to Eurocode 7. So it's a document sponsored by the Highways Agency to give additional recommendations to those already in Eurocode 7. Where does this leave the other British standards? Well, BS 8002, for example, is now withdrawn. It was originally nominated as non-conflicting complementary information. It's withdrawn, meaning that it is no longer being updated by BSI. That doesn't mean it doesn't exist, and you can in fact still buy it from BSI, and you may find complementary information in it that is useful. But where it is in conflict, Eurocodes take precedence. Syria C580, which is the document on embedded retaining structures, is also listed as non-conflicting complementary information. Hopefully that will be revised. It doesn't need very much revision. Hopefully it will be revised to be entirely consistent with Eurocode 7. The Foundations Code BS 8004 is similarly withdrawn, no longer a current British standard. So if you're being required to design to current British standards for retaining structures and foundations, you have to design to Eurocodes. They are the current British standards. On the other hand, when it comes to reinforced soil, BS 8006 has been revised and is still current, and that's been done because the Eurocode 7 has very little to say about reinforced soils. There will be in future a European document, but that's some way in the future. In theory, Eurocode 7 covers ground anchorages, but very inadequately, and therefore the British standard BS 8081 has been retained for the time being. Hopefully the European document will overtake that fairly soon. BS 6031 is still existing. It's been revised. There will in the future be a European earthworks document, but that's not coming yet. BS 1377 is being revised, really because sections are gradually being withdrawn as they're being replaced by European sections. And BS 5930, as I said, has been completely revised and is consistent with Eurocode 7, so that still exists. Let's move on to Eurocode 7 itself then. As a document, it comes in two parts. Part 1 is general rules with 12 sections and a lot of annexes, and to each Eurocode and each part of each Eurocode there can be a national annex. These are not allowed for other Euro norms, other European documents, but for Eurocodes there are national annexes. Part 2 has 6 sections and a lot of annexes which basically deal with testing methods, and again there's a national annex. This talk deals essentially with part 1, but just to say a bit more about part 2, its annexes mainly deal with testing methods, and they talk about how to derive parameters from those methods. This is not a document of how to carry out the tests. It's not a testing standard. It's a document written for designers, and it's the designer's involvement and interpretation of ground investigation and testing. Part 1 then has 12 sections and a series of annexes. The sections can be broken down roughly as shown here. The first 3 sections are fairly general. They would be used on any type of geotechnical job. General introduction, a basis of geotechnical design, which we'll spend some time thinking about, and then a section on geotechnical data, which very much relates to and somewhat overlaps with part 2. Section 4 deals with supervision of construction, monitoring and maintenance. This is the designer's involvement in those things. And whereas section 3 relates to natural ground, section 5 relates to artificial ground, fill, dewatering, ground improved or reinforced. Then we come to the rest of the sections, which deal with individual items that you might want to design: spread foundations, piles, anchorages, and so on, with a particular section 11 which is in some ways slightly out of place because you really need it for every type of design, looking at the overall stability of the site. In this talk we'll say a little about sections 2, 6 and 9. So coming on then to basis of geotechnical design, we need to think about limit state design, which all the Eurocodes are based on, and partial factor systems, characteristic values, and the issue of design approaches for ultimate limit states. To get a background, we need to go back to EN 1990. This introduces the terminology of limit state design, and it asks that you should look at ultimate limit states, where there is a loss of equilibrium of the structure, or it could be failure by excessive deformation or transformation of the structure into a mechanism, rupture. Essentially, these are all serious failures involving risk of injury or major cost. The aim of the design is to make them extremely unlikely, where the designer is required to look at the possibility of ultimate limit state, to analyze ultimate limit state, but then to make it an unrealistic possibility. So here's an ultimate limit state: a building has fallen over during construction, pulling the piles out of the ground. A deep station box in Singapore collapsed. Clearly ultimate limit states. Ultimate limit states are situations of, essentially of danger or of very high cost. Serviceability limit states, on the other hand, are situations involving the functioning of the structure in normal use, the comfort of the people, the appearance of the works, inconvenient, disappointing, usually a manageable cost and usually repairable. We want to make them rare, but it might be uneconomic to try to eliminate them completely. We get some settlement in a building, that's quite an old building, but here's a newer one being affected by settlement, repairable. Interesting to contemplate is what sort of limit state is this? Clearly the pier has settled an enormous amount. The bridge apparently is still in use, so maybe it's still serviceable. I think most people would regard that as an ultimate limit state. It's reached a dangerous situation. Eurocode 7 tells us to concentrate on 5 varieties of ultimate limit states, which go by these rather horrible acronyms: EQ, STR, GEO, UPL and HIDE. If we just take the outer ones first, really, EQ is about loss of equilibrium of the structure, considered as a rigid body, where strength of materials aren't playing a really big part in the problem. So for example, we have a balanced cantilever here, where we're really concerned about the balancing of two loads, and the intention is that, for example, that there would be no bending moment in the column here, and that the forces on the two piles would be equal, that both be in compression. However, a slight imbalance of the loads, even though those loads come from the same source, would clearly cause quite big bending moments and could put a pile into tension. So that has to be thought about in a very particular sort of way. Moving to the right of the diagram, these water-related limit states: uplift, in which we have simply a hydrostatic situation, but we have a buoyancy problem. That's a particular type of limit state to be considered. Or on the right we have a steady state, it could be a steady state, but with water moving through the ground, potentially causing internal erosion or piping. That's called a hydraulic limit state. These water-related issues have been important on a number of designs For example, in the Crossrail design basis, they considered the use of Eurocode 7, and it turned out to be particularly important to the design of some of the deep basements there, deep station boxes, where the question is, how do you hold the box down against water pressure? The thinking through the water-related issues was quite important to Crossrail. They found Eurocode 7 quite useful in that respect. Here's a paper written particularly about water pressures, design situations dominated by water pressure, which turn out to be quite difficult. It's difficult to think through the safety issues related to water pressures, and there's quite a bit of ongoing work in that area. I'll mention several papers during this talk, and they can be obtained by putting in a request to ARUPS for those papers. But primarily we'll be concerned in this talk about STR and geo, structural failure and geotechnical failure. Here are some diagrams that illustrate them. Geotechnical failure, for instance, could be a slope failing, perhaps taking a building with it, or a bearing capacity failure. Or here's another form of bearing capacity failure, just with an inclined load, or maybe sliding of a footing. Here we have a combined bearing and structural failure, and it's quite often really that STR and geo go together, and for many purposes they're just treated together, particularly for retaining walls, where we get a bending failure, for example, of a wall, but in conjunction with failure in the ground, an active wedge forming in the ground, or an anchor breaking, or other forms of structural and geotechnical failure occurring together. The fundamental equation for ultimate limit states, we will always be being asked to compare an E with an R, an action effect with a resistance. The second word that is used differently in Europe is the word action. An action is simply what in former British nomenclature we would have called a load. So loads are now actions, and an action effect is the effect of an action, the effect of a load in a structure. So it could be a bending moment, or it could be bearing pressure on a footing, where you've done a load takedown and found the what we might loosely call the load on the footing, the force coming to the footing, and that's the action effect on the footing. And we'd be comparing that with the resistance. The resistance could be bearing capacity, could be bending resistance of a beam or a column, or it could be a bending resistance of a wall. So E could be the bending moment in a wall, and R could be the bending resistance of the wall. We will always, in the end, be comparing a design action effect with a design resistance. You notice that there's no factor of safety given in that requirement, and that's because both of them are design values, design action effects compared with design resistance. That means they're factored values. The factors are already built into them. And the way that calculation is done is, in its simplest form, is to do a calculation represented by E here using design loads, design material properties, and the design geometry. So we do a load takedown of the design loads to get the force being brought down to a foundation, for example. And similarly on the resistance side, we calculate the resistance using the design material properties. So for example, we could calculate the resistance, the bearing capacity of a footing using the design strength of the ground. Design means factored, already factored. Question: why do we have, for example, why are there loads in the calculation of resistance, and why are there materials in the calculation of the action side of the calculation? Well, this side is easy. For example, supposing we're looking at the sliding resistance of a foundation, clearly the vertical load coming onto that foundation in a frictional material will affect its sliding resistance. So we have to have the loads on the resistance side. And similarly, if we're trying to calculate, let's say, the force in a strut, the strength of the ground will affect the force coming to the strut. So we find strength terms on the action effect side. Mainly it's because we're dealing with frictional materials, and with frictional materials the forces and the material properties have to be considered together in many cases. In its simplest form then, the design values of the loads are so-called representative values times a partial factor. The design values of the materials are characteristic material strength divided by a partial factor. And that begs the question, what do we mean by characteristic strengths of materials? And leads us on to the question, what are characteristic values of material properties? Basis of design tells us that we will find design material properties by taking characteristic values, dividing by a partial factor gamma m, and possibly multiplying by a factor eta. Eta is a conversion factor, taking account of volume, scale effects, moisture, temperature, and so on. In other words, eta is a factor to convert what you might measure in a lab test to what you expect to be really there in your real structure. Gamma, on the other hand, is a safety factor to take account of the variability of the materials. But it tells us that in appropriate cases this eta factor, this conversion factor, may be implicitly taken into account in the characteristic value itself or combined into the gamma. And very subtly they change gamma little m to gamma capital M to show that the eta has been combined into it. We'll see what that means for geotechnics in a moment, as we come into basis of geotechnical design in Eurocode 7. So to find out about characteristic values, we'd read that chapter, and we'd read a lot of words about characteristic values of soil properties. The basic definition of characteristic values is given here. The characteristic value of a geotechnical parameter shall be selected as a cautious estimate of the value affecting the occurrence of the limit state. There's some important words in that. It is to be selected. That means it's a human activity. There's human judgment in this process. The aim is to provide a cautious estimate, not the engineer's best guess, but something the engineer is reasonably comfortable with, being cautious. It's a cautious estimate of the value affecting the occurrence of the limit state. So it's not a cautious estimate of what you expect to get in a laboratory test. You'll use laboratory tests to come to that cautious estimate, but it's a cautious estimate of what you really expect to be happening in the ground, governing the way the ground behaves. So important words in that definition. And then the rest of that clause goes on to expand on that a bit. So in paragraph 4 there, we see some of the things we're supposed to take account of, and this is in the selection process by the engineer. He's to take account of geological and other background information, such as data from previous projects. This is good engineering. He's got to think through what is all the information I know that I can use to judge my cautious estimate of the strength of the ground. He's to think about the variability of the measured properties. How variable were all the lab test results, for example, if he's got them, other relevant information for existing knowledge. How extensive was the field and laboratory investigation? Have I got many test results or only very few? And what is the extent of the zone of ground governing the behaviour? Am I reliant on a little bit of ground or rather a lot? Here's an example of that. I have a building to be constructed at the top of a slope. So I'm concerned about slope stability and I'm concerned about bearing capacity. Let's suppose these are estuarine beds, so we've got mainly sand, but we've got some clay lenses in it that we're a bit concerned about. If I'm looking at an overall stability, it can't pass through very much of the clay. It's mainly dominated by the sand. So I can take an average and perhaps take some account of the clay, but it's basically the strength that I'm interested in is the strength of the sand. On the other hand, when it comes to thinking about the bearing capacity, is it possible that some of the footings could be dominated by a clay lens? Have I eliminated that possibility? If I haven't, then I have to design the footings for the clay. And the characteristic strength of these beds would be different for the footing design from what they would for the overall stability design. On the other hand, again, I might say, well, I'll eliminate that possibility because I'll probe every footing situation. And if I find some clay, I'll dig it out. So I'm now sure that it's sand. And again, I can take a much more optimistic view of the ground conditions. So it depends how you do the investigation, and it depends on the size of the zone of ground. Will it average out a lot of these things, or will it not be able to? Or again, here's a cone penetration test. Suppose I'm going to design a pile in this situation. For the shaft of the pile, it will average out the low points and the high points. So I can afford to take an average penetration resistance as I think about the shaft resistance. On the other hand, the base resistance of the pile will either be in soft material or in pretty good material. So I need to think about how thick is this layer of good material. Can I drive into it and be sure that it's then going to be the dominant stratum for the base? Or is it rather thin? Are we going to go back to some weaker material below? And this would affect the choice of characteristic strength for the base, and it might be very different from that for the shaft, which is taking an average. We're also told that in this cautious estimate that we have to make, we have to think about the fact that many parameters are not true constants. They depend on stress level. We have in soil and particularly in rocks, are there fissures, joints that have to be considered? What about time effects, softening, brittleness and ductility? The method of installation of the structure, effect of workmanship, and generally the effect that the construction activities may have on the properties of the ground, because we're asked to estimate the value that would affect the occurrence of the limit state. If the construction changes the ground, then that's all part of this estimate of the characteristic value. For example, we may have a nice dense sand, but we're then going to bore some piles in it and loosen it all up. It will change its properties, and that has to be considered in the characteristic value. What we're really doing here, coming back to this EN 1990 business, is to take these implicitly, we're taking account of this conversion factor eta in the assessment of the characteristic value. So far I haven't mentioned statistical methods at all, and Eurocode 7 says that you might find statistical methods useful, but be very careful with them. If they're used, make sure that you're not throwing away any knowledge. You're not throwing away a priori knowledge of what happened on the next door site or what you can read about this stratum simply because you've got a few test results and you can do some statistics. That would be a dangerous path to go down. But if statistical methods are used, then the aim of that process is that the probability of a worse value governing the occurrence of the limit state is not greater than 5%. If you like, this quantifies the statement that you're taking a cautious estimate. You want a value that such that its effect on the limit state would be not greater than 5%. So generally, the characteristic value is not a fractile of test results. Certainly not a fractile of test results. It may be a probabilistic aim for what's in the ground. It's a cautious estimate of the value affecting the occurrence of the limit state. It's to take account of time effects, brittleness, soil fabrics, and so on. And really all the designer's expertise and understanding of the ground is encapsulated in the characteristic value. Considering both project-specific information and a wider body of geotechnical knowledge and experience. Thinking through all that, it's really rather the same as what in other codes, in Syria codes, are called moderately conservative values. BS 8002 called it representative. I think it's what good designers have always done. And interestingly, some work has been done on this, suggesting that characteristic values may be something like a 5% fractile of mean values. That's what you're looking at. 5% probability of the average value averaged over quite a lot of ground. Very different from a 5% fractile of test results, which is what's used in structural design. 5% fractile of mean values, if you were to do a normal distribution, if you got a normal distribution of soil test results, would lie at about half a standard deviation from the mean of the test results. You have to use a more remote value than that if the failure mode doesn't average a lot of ground. American work looking at a similar problem has suggested that a good way of estimating what they call a conservatively assessed mean, rather similar thing, is to take a 75% exceedance value. In other words, 75% of your test results are better than what we would call characteristic value. That's quite a good guide. I think it's a useful guide to look at, but not a hard rule. Another issue we find in section 2 of Eurocode 7 is this business about design approaches, and we must look now briefly at that. Again in section 2. Before we do that, we can perhaps look at some of the later sections. Eurocode 7 doesn't limit you to designing by calculation. It has other methods, prescriptive measures, designed by load tests, or the observational method. So the observational method, for example, is a method in which you can start to make a construction, perhaps on a slightly more optimistic view of the data. You will have done some calculations, but not limited quite so much in your pessimism, on the basis that you're going to monitor and can react if things start to go wrong. So you'll have established what are the acceptable limits of behaviour. You look at the possible range of behaviour, you'll plan the monitoring, and you'll know you've got enough time to respond and introduce contingency actions. During construction, you do the monitoring. That's really a very important, obvious but very important statement. You will assess the monitoring and you will react. Importantly, you will replace any monitoring equipment that fails. This approach has been taken up in British practice by the Syria report on the observational method in ground engineering. And the Eurocode 7 requires the production of a geotechnical design report. It is a code requirement that you produce a report clarifying what you've done in the design and stating where you got the data. Now I want to come back to geotechnical design by calculation, which is quite a long section, as you see here. It goes through what we've already covered on characteristic values, how we'll derive design values from those, and then talks particularly about ultimate limit states and serviceability limit states. We'll pick up serviceability limit states first. For serviceability limit states, the requirement is often slightly different. It's that the effect of a structure shall be less than some limit, it's called here CD. So this could be the effect of the loading rather is a calculated settlement, for example. There's got to be less than a limiting settlement. That quite often would be the approach. On the other hand, and that approach is given out here. A limiting value for a particular deformation is the value which is serviceability limit state of a serviceability limit state. It could be acceptable cracking or something like that. So that would give you a value of CD, clearly a value to be discussed with structural designers, and not really a value that can be specified by the code itself, limiting settlement and deformation. For serviceability design, all the partial factors, in theory they are all there, but their values are unity. Generally, the National Annex could decide not to use unity, but in general that's always done. As an alternative to calculating deformations as such, you may verify that a sufficiently low fraction of the ground strength is mobilized. So this is looking at mobilization factors, if you like. For these type of calculations, various Oasys programs are available. PDISP, often used for calculation of settlement, XDISP for settlements around excavations, or FRU for movements of retaining walls, ALP for displacements of piles, or SAFE, general finite element analysis, for settlements, movements of retaining walls, and so on, a whole range of possibilities with finite elements. Coming back to the fundamental requirement, these are mainly considered for ultimate limit states. We've talked about the action effect being less than the resistance. We introduce factors, but there are different ways of introducing the factors. The Americans prefer to calculate unfactored resistances, bearing capacities and so on, and then factor the resistance. And this option is also given in Eurocode 7. Similarly, on the actions side, it's possible to do the load takedown, collect all the actions together, and then factor the action effect instead of factoring the individual actions. So in total, we could have the factors outside these brackets, factoring the effect and factoring the resistance, or inside the brackets. And you can see that there are various alternatives here. Various Oasys programs can be used for these calculations, and the alternatives have led to 3 different so-called design approaches being available in Eurocode 7. The design approach is a national choice. Very briefly, design approach 1 requires you to do 2 different calculations, to check every ultimate limit state by 2 separate calculations. In the first calculation, the loads are factored, but the material strengths aren't. In the second calculation, the loads are barely factored, just a small factor on variable loads, and we factor material strength instead. Slightly different approach is taken to piles and ground anchors. In design approach 2, the loads are factored and resistances are factored, and that's done simultaneously. It's all in one calculation. But unfortunately, it's found that Design Approach 2 is limited in its applicability. And so the countries that have chosen to use Design Approach 2 find they have to have other add-ons as well. Design Approach 3 is a system which factors loads and material strength and basically doesn't really factor resistances. So there are different ways that the factors are put together. Now, the choice of Design Approach is a national approach, and the UK choice is Design Approach 1, factoring separate calculations are called two combinations, factoring the loads with unit factors, the green cells mean unit factors on everything else, then a separate calculation, small factor on variable loads, and factoring the material strengths. Different approach for piles and anchors. The reasons for these choices are written up in a paper that is available. Approaches to ultimate limit state design, the merits of Design Approach 1. Basically, the reasoning is that if you look at a problem like this one, here we have a structure, it has foundations, it's affected by slope stability. This retaining structure was used to prevent a slope stability problem. So we've got a foundation, slopes, retaining structures. They're really all part of the same problem. And in this particular case, as a practical case, the slope and retaining wall being part of the same problem, they just have to be designed together consistently. There are benefits when you have these sort of combined problems in using two separate combinations. It avoids too much conservatism in the design, and generally the preference in Design Approach 1 is to factor the parameters before they're combined. Again, this is really because it's a much safer system to do that. Finally, Design Approach 1 is good for finite element analysis. Design Approach 2 it really can't be used with finite element analysis, so its use for future development seems rather limited. So with that background, let's look quickly at some examples. Here's a very simple spread foundation example we'll come to. What's in the code first of all. The spread foundations come in a variety of forms. They may be a simple pad foundation, but even a simple pad foundation may have inclined loads on it. That pad might actually be the foundation of a retaining structure. We might have a very simple pad foundation here, or that could be a big raft beneath a structure. All of those are spread foundations. Let's look at a very simple pad here, just to get the principles sorted out in our minds. Very simple. It only has a permanent load, no variable load, no inclined load. Remember that we will have to do two calculations, one with factored loading, one with factored ground strength. Annex D of Eurocode 7 provides bearing capacity factors for the ultimate limit state calculations. Here's the familiar bearing for capacity factor calculations, originally given the name, but following the name of Terzaghi, with the bearing capacity factors here, with allowances for load, inclination, shape of the footing, and so on. But we have the NC, NQ, and N gamma terms, and the code actually gives you formulae for those factors, which you can easily use in a spreadsheet. And if we use those factors, we could carry out a bearing capacity calculation. If we look at combination 1, we would have factored the loads but not the material properties, so we'd get NQ and N gamma in this case from the characteristic angle of shearing resistance here of 35 degrees, and we could compute that the width of the footing had to be just over a meter, and the bending moment in it 197 kilonewton meters, 179 kilonewton meters. When we do combination 2, on the other hand, we'd get a different width for the footing. We'd find it had to be wider, lower bending moment. how are we going to deal with that? Well, our final design has to be able to comply with both requirements. So the width of the footing has to be 1.31 meters at least. But it also has to be able to take the loading of design approach 1. So now we have to consider the wider footing, combination 2 width, with the combination 1 loads. And now we get a bigger bending moment, 221 kilonewton meters. So at this stage, if we only have to consider ultimate limit states, we have a 1.31 meter wide footing, and there's the design ultimate limit state bending moment. That's the bending moment for which we do ultimate limit state bending check in the footing itself. And we have to do that. The assumption here was that there is a uniform distribution of bearing pressure beneath the footing. You're told in the code to do that for structural design, unless you want to use some clever means of allowing for the flexibility of the footing, which you might do for a big raft, but not normally for a pad footing. Here's how those calculations would have looked. We have our characteristic vertical load here. In combination 1, we're going to multiply that by 1.35. So by the time we've also added on the weight of the footing itself, that comes to, the 1,000 has increased to 1386 kilonewtons. On the other hand, we have our 35 degrees, and the factor we apply to that is only unity. So the design angle of friction for the calculation is 35 degrees, and we use that to calculate the NQ and N gamma terms. We then go through the calculation with no load inclination. We have some allowance for the shape of the footing, which is square, and here we've made a guess at the footing dimensions and calculated a bearing resistance, which we have to check is bigger than the vertical load. It is, so we could use a footing of about that dimension, and that's how we derived the bending moment here. Combination 2, on the other hand, we start again from the vertical load of 1,000 kilonewtons. We have a unit factor on permanent load, so even though we've added the weight of the footing, the load is still only 1033 kilonewtons here. But now the 35 degrees has to be factored down by a 1.25 factor, and so the design the design angle of friction is 29.3 degrees, giving us lower values for NQ and N gamma, lower than we had when it was unfactored, which means that the design resistance of the footing, even though we've assumed 1.31 width, the design resistance is only 1031. Well, good enough for 1033, and therefore we can live with a 1.31 wide footing with our bending moment of 164 kilonewton meters. But as I said earlier, we have to check the 1.31 wide footing with the load factored up, and now including the weight of the footing itself, it comes to 1386, and we get our bigger bending moment. That's how the calculation would run. I've added there also the design approach 2 and 3 calculations, just so we can make a comparison here. And this is typically the sort of result that we get, that when we look at the two combinations for design approach 1, when we put the two together, the width is shown here. That was our 1.31 meters. For design approach 2, we get almost the same width, slightly less in this case. Design approach 3, slightly more. Generally speaking, we'd find that design approach 2 would give much the same result as design approach 1, usually rather more conservative with design approach 3. Bending moments also fairly similar for 1 and 2, usually a little bit bigger for 3. So that's a comparison. But the British code, the British National Annex, requires only design approach 1. Now, all of that was for ultimate limit states. But of course, we've got to check also the serviceability limit state. And for spread foundations, we might often find that we would want to make them bigger to prevent excessive settlement. So in this case, for example, we may well find that we wanted to have a 2 meter square footing to get the working bearing pressure down to about 250 kilopascals and therefore give reasonable settlement. If we do that, if we increase the size of the footing, we need to recheck the bending moment for structural design. If we were to check it with the combination 2 loads, we get 250 kilonewton meters now, and the combination 1 load leads to 326 kilonewton meters. This is a factored load. So the structural design in this case for a 2 meter square footing would use 326 kilonewton meters as the design bending moment. No further load factors on that into the structural design. Now that may all seem a bit contorted, but actually if you think about it, I think it is just a standardized way of doing what probably we've always done in design of such a footing. We've thought about its ultimate bearing capacity, we've thought about its serviceability, its settlement requirements. Quite probably the settlement requirements have given the size of the footing. But at any rate, it's the geotechnical requirements give the size of the footing. Having got the size of the footing, we then apply factored loading to get the bending moment for structural design. And essentially that's the process that we've gone through there. Size coming from the geotechnics, either serviceability or combination 2, and the factored loading coming from combination 1 for structural design. The final design must satisfy all the criteria: ultimate limit state, 2 combinations, and serviceability limit state. You remember that, or in fact, section 6 carries on the points made in section 2, making it clear that calculations may not always be necessary for serviceability. If necessary, calculate displacements, and if you do that, PDISP is the Oasys program that would be exactly the right thing to use for that purpose. I just point out here that pad foundation, spread foundations may well be not for structural pads, but for the base of a retaining structure. And here, of course, we do get eccentricity of loading, inclination of loading becoming important, and those will start to affect the values of the bearing capacity factors. You can see over here, inclination factors in particular for inclined loads can halve the bearing capacity quite readily. This wasn't properly spelt out in BS 8002. I think it's a much clearer presentation in Eurocode 7. And here's just a practical application, somebody doing a retaining wall calculation. They've just set it up in a spreadsheet to do the calculations for them. Here's another job on which Eurocode 7 was used. It's not in Europe as it happens, but Eurocodes are being used internationally. This was the Grand Museum in Egypt. Here it was governed by serviceability, and that will often be the case for spread foundations. But on the other hand, pad foundations for design at Coventry University, you can see the pads, it's all on shallow foundations here, shallow spread foundations. This was founded on sands and clays, interbedded sand and clays, and found to be governed by the long-term bearing capacity in the ultimate limit state. What you do find for structural design is that a very careful consideration of all the relevant load combinations is necessary, because the structural designers are being taken through, in the Eurocodes they've been taken through load combinations quite carefully. They have to be clear about them, and it's very important to get good communication between the foundation designer and the structural designer to make sure who's applying the factors and where, particularly the partial factors. Are the loads coming from the structured factored loads, or are they not? But that building is under construction and I think will look very nice. Let's move on to retaining structures. So section 9 of Eurocode 7 deals with retaining structures. Here are its subsections. Most of the sections are set up in this way. They have a general introduction. They talk about the limit states that are relevant. They talk about the actions that the structure will be subject to. Normally a section on design and construction considerations. This is partly its constructability, what the designer must be aware of in the process of design. And then some special sections. Here's one on determination of earth pressures and water pressures, and usually sections on ultimate and serviceability limit state design for those particular structures, retaining structures in this case. So the code is pretty strong on checklists, and it recommends that you compile a list of limit states, the limit states that the structure might be subject to. And it splits those up actually for gravity walls and embedded walls, and takes you through that. It's a very useful checklist just to work through and make sure you've covered everything. Geometrical data is particularly important for retaining structures, particularly the ground surfaces for excavations in front of retaining walls. Geometrical data are particularly important for retaining structures, and some special requirements have been introduced. Here you see that that for ultimate limit state calculations, not for serviceability, in cases where the stability of the wall depends on the ground resistance in front of the structure, the level of the resisting soil should be lowered below the nominally expected level by an amount delta A. So we're going to lower the surface of the passive soil. For a cantilever wall, delta A should be 10% of the wall height, limited to 0.5 meter. For a supported wall, delta A should be 10% of the distance between the lowest prop and the excavation level, limited to 0.5 meter. This is the same requirement as was in BS 8002 in its latest form. So for a cantilever wall here, we lower the surface by 10% of the wall of the supported height. For a propped wall, we lower by 10% of the distance below the prop. Smaller values of delta A, of this allowance, even 0, may be used when the level surface is specified to be controlled reliably throughout the appropriate execution period. In other words, if the surface is very well controlled, you can decide not to make this allowance. It says that you should make this allowance with a normal when there is a normal degree of control. It's only when it's exceptionally well controlled that you're allowed to omit it. Design and construction considerations look at the requirements for related to the construction of the wall itself. An important one here is to think about the ductility or brittleness of the structure. Retaining walls should be designed in such a way that there are visible signs of the approach of the ultimate limit state. should guard against the occurrence of a brittle failure, with sudden collapse without conspicuous preliminary deformations. And then part of these construction considerations, the designer needs to think through the provision of the temporary support, the changes to the in situ stresses that will have effects on surrounding constructions, the effect of constructing the wall itself, disturbance of the ground due to driving and boring, and so on. The degree of water tightness is not strictly part of a Eurocode requirement. Eurocodes are concerned with the strength of the structures rather than the water tightness. And here come the constructability things, the practicability of constructing the wall to reach the appropriate stratum, the practicability of forming the ground anchors if they're going to be used, and so on. Drainage systems, walls often depend on drainage systems, and the words that are used here is that one of the following conditions must apply. Either you have a maintenance program, so you have access and you can maintain the drainage system, or you demonstrate both by comparable experience and by careful assessment of the water discharge that the drainage system will operate adequately without maintenance. This is pre-assessment before you build the thing, but it's looking at the in other words, it means a very careful design of filters, and also considering the chemistry of the water and whether there will be any clogging due to biological effects. But having done all that careful assessment, then also to say I've got comparable experience to show that this will be okay, and without that you're not allowed to proceed without a maintenance program. Coming on to the section on determination of earth pressures, wall friction is a very important topic, and you have to think about the strength parameters of the ground, the friction properties of the ground wall interface, and the direction of movement of the wall relative to the ground. We'll come back to that in a moment, but having thought through those things, you're limited by an angle of wall friction delta, and what it says is that the design value of delta it has to be related to the constant volume angle of wall friction, or the critical state angle of friction of the ground. What this is really saying is that we assume that the ground immediately adjacent to the wall has been disturbed, and the same is said for pad foundations for sliding. The ground immediately adjacent to it has been disturbed, it's in a loose state, and you treat it as loose material. You're allowed to go up to, for precast or steel walls, you can go up to 2/3 phi CV, so if you like, that's delta over phi of 2/3. For concrete cast against the soil directly, you can go up to unity. That's quite a relatively higher value of delta over phi than has normally been used in British practice in that particular case. The code provides limiting values of earth pressures, but makes this is coefficients of active and passive pressure. Makes the point that you're not to use straight line failure surfaces. In other words, the Coulomb methods are not to be used. What you are to use for calculation of coefficient of active pressure are methods of Kako-Kerisel, Sokolovsky, or methods given by Eurocode 7 itself, which use curved yield surfaces. You're more critical than the very simple Coulomb calculations, which are unsafe. And those values are provided in Annex C of Eurocode 7. It provides both charts and formulae for coefficients of active and passive pressure. Note that this annex was considerably revised in January 2010, so you need to make sure you've got that amendment in using Eurocode 7. It has charts which looks like this, which are basically the Kakko-Caricel numbers. They are very widely used. If wall friction is acting in the wrong direction for you, they don't provide any numbers. What do I mean by that? Well, normally we expect that wall friction would typically be acting down on passive soil and up on the active side. So this figure shows it. The wall is pushing upwards on the ground there as this soil slumps below the wall. The wall is pushing down on the ground there as the soil comes upwards. If that isn't the case, then Kakko-Caricel don't provide the numbers. And adverse wall friction may be caused by loads on the wall from structures or inclined ground anchors. Annex C also provides some programmable formulae. They're not simple to use. They're built into the Oasys software through and Starwall. It's quite tricky to check exactly where they came from, but there is a paper in Geotechnique by Lancialotta which gives exactly the same numbers, and it's easy to follow his analysis. And they cover a wider range of wall friction. The results are slightly more conservative than Kakko and Caricel, especially when phi and delta over phi are fairly large, but perhaps they're more correct. The charts are also available, or charts are available representing those formulae in the commentary by Simpson and Driscoll. It's the only place they're published, I think. But or were published, but now they're in the concise Eurocode 7, which has very recently come out. Simpson and Driscoll also provide a comparison between Kakko and Caricel and the charts, and you see here that for when delta over phi is fairly high and phi is high, then on the passive side Kakko and Caricel give considerably higher values, 130% of the value found from the formulae in Eurocode 7. So Kakko and Caricel potentially unsafe, I think, in those extreme cases. Annex C also provides some relationships between movement and the development of earth pressure, and that again has been revised quite recently. Importantly, Eurocode 7 allows you to use calculation methods which redistribute earth pressures. And we'll see what that means in a minute. These little figures have been quite popular from Eurocode 7. These are figures showing the failure modes that you're to consider, overall stability modes, more overall stability, and then the failure modes of the wall itself with active wedges and passive wedges, how it might rotate about a prop, a low level prop, and particularly vertical equilibrium. And this is where adverse wall friction starts to come into play. Let us suppose that we have a wall here. We would normally expect that the ground would be pushing up on the wall would be pushing down on the soil in the passive zone. The wall would be pushing up on the soil, the ground would be pushing down on the wall here on the back of the wall as the soil moves downwards. That's what we'd normally hope for. But it's not always the case, particularly if we have vertical loads coming onto the wall and inclined ground anchors, for example. In that case we get a reversal. We get the ground pulling down, or rather we get the wall pulling down on the soil and the soil having to hold the wall up. this is what we've called adverse wall friction, because it tends to increase, for example, the active pressures quite considerably and reduce the passive resistance if it happens on the passive side. So it's very important to think through the vertical equilibrium of the wall, and what is very significant here is to make sure that any calculation for vertical load carrying capacity is done consistently with the design of the wall as a horizontal load taking member. So a whole series of pictures for ultimate limit states. Must think about compatible deformations and the reduction in strength due to that deformation. There are some figures here for failure of ground anchors, and it refers to section 8. Note that section 8 shouldn't be used, it is being revised. That's the section on ground anchors. For serviceability limit state, the code says, well, you can calculate displacements. You should think about earth pressures related to displacements for serviceability. You should always make a cautious estimate of the distortion and displacement of the walls, probably based on other experience. If there is doubt, having made that estimate, or if it exceeds the limiting values, then you have to go into calculation. So note that the code isn't forcing you to calculate displacement here in many cases, but when you have to, then you need some sort of computer program probably to calculate. Let's look then at a propped wall, design of a propped wall 8 meter high. We're going to have a prop in at 2 meters depth. We've got some material properties here, K0 where it's relevant. We could do a very simple design just using simple active and passive pressures. This would comply with the code, and the calculation for it is rather similar to that bearing capacity calculation we looked at earlier. We start to factor the angle of friction in combination 2, so we design for a lower angle of friction, but in combination 1 we have a unit factor, so we design for the full angle of friction, and we derive active and passive pressure coefficients from those factored or unfactored angles of friction, and we'd also think about serviceability unfactored. When we do that, we calculate the wall lengths. We have to use the longer of the two wall lengths because that we have to comply with both requirements, and in this case we'll normally find that it's combination 2 that'll give us the wall length and the biggest bending moment for structural design. We do the serviceability unfactored calculation, maybe using different software. We'd get other bending moments to consider for serviceability. So for crack widths, for example, we'd look at these lower bending moments. Probably in this simple example we might use star wall for the ultimate limit state and FRU for the serviceability limit state. But remember that the code allows us to redistribute bending moments, and on that basis we may well use FRU for both for ultimate limit states as well. Here's the possibility of redistributing the earth pressures as a result of deformation from the simple linear case. We'll look at the result of that in a moment. Syria 104, just for a comparison, required you to use linear earth pressures, and it said use those earth pressures to calculate the length of the wall, here about 20 meters. And if you do that, this is with factored soil strength, you get a high bending moment. But then it said, well, disregard that bending moment. Do an unfactored calculation to get a bending moment and multiply that by 1.5 and get a lower bending moment, and use that for the bending resistance. This is really a rather incompatible and inconsistent way of calculating, because the bending moment you're designing for really isn't big enough to use the length of the wall that you've determined to be necessary. Eurocode 7, on the other hand, would allow you to redistribute. One way to do that would be with a finite element analysis. And if you do that, you can calculate a bending moment from the finite element analysis. What I've collected together here is a whole series of results. Star wall with the simple linear analysis, through with the as the Oasys method of redistributing bending moments, or the finite element analysis with Oasys. And I simply want to make the point here that when you use the methods that allow redistribution of bending moments, the final design bending moments come out relatively low. Without redistribution of bending moments, we get rather high bending moments, much higher than we would have used with Syria 104. So using Eurocode, you really need a calculation that redistributes the bending moments. And there's a comparison showing the same thing. Good design by Eurocode will have redistributed bending moments, and when you do that, you can probably get a rather shorter wall than you would have had in previous practice. But designing the wall is not the whole of the story, or finding the bending moment is not the whole of the story. You then need to find, for example, the steel section that you will use in design. And to do that, you need to move to Eurocode 3 Part 5, for example, for a sheet pile wall. Eurocode 3 Part 5 divides sheet piles into 4 classes. Well, it's really 3 classes, because classes 1 and 2 are the same sheet piles. They're good, stocky, strong sections, which we would probably have used in most traditional practice. And for those, it allows you to use plastic design and gain some advantage by plastic design. And it says that you can, or it has been said that you can get economies of up to 30% by using plastic design of sheet piles. Here's the rules it gives that allow you to classify the stiffness of your sheet pile section. Now we'll show very quickly an example of how that might work in Oasys software in a moment, but it's important to make the point that sheet pile manufacture is changing because higher strength steels are now being used. As higher strength steels are used, the sections are less stocky than they were. And consequently, although it used to be the case that most sheet pile sections would conform to classes 1 and 2, it may not be the case in future because the steel sections are thinner, though of higher strength. Here's very quickly as an example of how you might do such a design. This was a sheet pile wall design done in Fru, so we take it through some stages of excavation and calculating bending moments here, calculating displacement and bending moments. You see in this particular case, as we've made the full excavation, we've got well, we're getting up to a bending moment of approaching 400 kilonewton meters here. I'm sorry, I'm misreading that from the scale. Here's the moment at the bottom here. It's whatever, 500 or so. We put in an extra prop. We take the excavation deeper. And then what we've looked at in this particular case is, let us suppose that as we are starting to refill, we're putting in the permanent props here, we want to take a prop out. This quite often happens, and quite often at that stage you get a computed bending moment which is much bigger. We're approaching 625 kilonewton meters per meter. Let us suppose that the sheet pile section couldn't actually take that, and we want to cut it down to something like 450. With the rules in EC7, EC3 Part 5, it might be possible to do that by plastic design. if we allow a plastic hinge to form. So here's an analysis in which a plastic hinge has been able to form simply by making a section relatively soft, a short length of the wall, able to deflect more readily. You're required then to calculate how much rotation occurs at the hinge. Although it looks horrific here on this exaggerated scale, it's actually quite small, and it's well within the limits of EC3 part 5. And you see what's happened to the bending moment. It's dropped at this level but increased at the prop, so now you have to check it at both locations, and it's around about 400 kilonewton meters per meter in both cases. Note that it may be more critical here. The bending moment requirements are more critical at prop position, where there's large shear forces, than they are at mid-span. So the important place to check the bending moment would probably be here. Whether this process will be acceptable in the future with more flimsy yet stronger sheet pile sections remains to be seen. Only refers to ultimate limit state calculations. You can't have plastic design at serviceability level. Well, to conclude this talk, some references. Here's a list of documents that you might find useful. Very old code now, a very old commentary now on Eurocode 7, but it is available for free download, for instance, on the Construction Information Service website. Thomas Telford have produced a whole series of design guides. Here's the one on EN 1990, and they're on 1997. They're useful documents. Free download Design a Simple Guide on the government website, and there's a Syria guide, all of these providing different useful information. Probably the best textbook is the one by Andrew Bond and Andrew Harris, Decoding Eurocode 7, which you can buy, and I've given you there a lot of web addresses where you can find information. Finally, down here, two recent publications from BSI, Concise Eurocode 7 and Eurocode 7 Online. Both of these have commentary, and in particular Concise Eurocode 7 is a cut down version of Eurocode 7, cutting out the parts that you wouldn't use so much but adding quite a lot of commentary, and I have to claim some responsibility for this, I'm afraid, but that's now available to be bought from BSI. And finally, there is a website, eurocode7.com, on which you can find some design examples spelt out for you. It might tell you at some stage that you need a password, but don't worry, you don't actually need it. And you can download a whole series of design examples there. Well, I hope you've enjoyed this talk and found it useful, and thank you very much for your attention.